Hello, my name is Julian Bautista. I'm faculty at Aix-Marseille University in France, and I'm happy to talk about the DESI Peculiar Velocity Survey and the first growth rate measurements with DR1. This is the plan of my talk. I'll start introducing why we're interested in measuring peculiar velocities. Then I'll go in detail on the DESI Peculiar Velocity Survey and our results, and finish with some words on what's next for the near future. Why we're interested in peculiar velocities? Well, we want to test what's causing the accelerated expansion, whether it's dark energy or modified gravity. Dark energy, it's currently in this situation, as you probably seen this plot already. There's a strong tension with lambda if you consider the W0 WA extension for dark energy, when you combine different cosmological probes to the level of 3 sigma. So we want to understand this, or maybe we need to modify our theory of gravity, which is GR, and there are many different ways to do this. There's families and families of models that can modify general relativity to try to explain the accelerated expansion. So one way to test whether it's dark energy or modified gravity is to look at the growth rate of structures, looking at how perturbations grow with time. In this parameterization, this gamma, the growth index, is equal to 0.55, but we can try to measure this and quantify deviations from this theoretical prediction. What about peculiar velocities? Well, peculiar velocities are related to this growth rate of structure. From the continuity equation, they are related to the density field with this expression. And if you go to Fourier space and compute the power spectrum, you see that they're related, the power in velocity is related to the density one, which is proportional to sigma 8 squared times f squared. There's also 1 over k to squared factor here, saying that most of the amplitude of the velocity field is on large scales. So if we measure peculiar velocities, we can have measurements of f times sigma 8, and we can test the GR prediction. The usual way to do this is with redshift surveys. I'm displaying one example of a galaxy redshift survey here, where at each point is a galaxy, and you see how clustered they are. And I'll also show in color scale the velocity field. And you see that the velocity field correlates on much larger scales. They're coherent over larger scales than the clustering of the points themselves. That's the 1 over k factor that you saw in the previous slide. So looking at the statistics of the density field distorted in redshift space, you see anisotropies in the spatial correlation functions, and then you fit using templates the value of f sigma 8 using this technique, and from f sigma 8 and Alcoy-Paczynski parameters you can derive cosmological parameters. Of course, there's more recently we developed techniques to go directly from spatial correlations to cosmological parameters. Those are often called full shape fits or CMB-like analysis of LSS data. Here are the results from past measurements from surveys on RSD of f sigma 8 versus redshift. Here I'm putting on log scale. You're going to see y next, but here I was just using the density fields and showing SDSS points and DESI compared to different theoretical models, the solid one being GR. But if you can see that at low redshift we have smaller volumes, and particularly we see that uncertainties get larger because we have cosmic variance that's hitting us hard there. So the idea of measuring peculiar velocities is that you have an extra field like this for a fraction of those galaxies, and you can do some sort of 3 times 2 point function with this velocity field, including the cross correlation with the density, and that gives us better constraints on growth and cosmological parameters. So there are many past measurements that happened with different surveys, different methodologies. They all give different results. And our talk is about this measurement here. There are 4 points. I'm going to go more into detail next. But the consensus, we use 3 different methodologies, and we have a consensus result that is given by this point here. And you can see that those uncertainties are already much smaller than those obtained by RSD only. Okay, so now I'm going to talk about the DESI Peculiar Velocity Survey and the year 1 results. To obtain peculiar velocities, we need to combine spectroscopic redshift with a distance indicator. The distance indicator is a probe of the cosmological redshift of the galaxy that does not depend on this one, and combining the two we can obtain the radial peculiar velocity. There are a few distance indicators that have been used in peculiar velocity studies, such as the Tully-Fisher relation, fundamental plane, and type 1a supernovae. The Tully-Fisher and fundamental plane relations are empirical relations using galaxies themselves, so they have quite large intrinsic scatter of about 20% in distances, while type 1a supernova we know are better standard candles. They have much smaller uncertainties. There are future data sets here. Here are some numbers, and DESI is planning to measure both Tully-Fisher and fundamental plane relations. So I'm going to go more in depth on this one. Tully-Fisher relation is about the rotation, the link between the rotational velocity of a spiral galaxy and its absolute magnitude. So in DESI, we can place fibers either at the center and at the edge of the galaxy, and the difference in the redshifts measured, which is small, is due to the rotation of the galaxy. And we can link those measurements to the absolute magnitudes and obtain peculiar velocities from those. Here are some other examples of galaxies that we used to test the methodology, placing either 2 fibers or many fibers to see where to place best the fiber to optimize signal to noise. On the other hand, we have the fundamental plane relation. This concerns elliptical galaxies, and the idea is that we place a fiber in the center to get a very high signal to noise measurement of the dispersion of the velocity dispersion of the stars in the central regions, and that's given by the width of the absorption lines. So combining this measurement with the surface brightness from photometry, that gives us an estimate of the actual physical size in kiloparsecs of the galaxy, from which we can convert to an angular diameter distance measurement, and therefore a peculiar velocity. Here's the footprint of DESI in gray compared to past famous peculiar velocity surveys such as 6DF, Cosmic Flows 4, or SDSS PV. And this is the redshift distribution. You can see the very low redshift range here for those tracers, and the reason is that the contribution of the peculiar velocity becomes quite small compared to the cosmological one if you go to higher redshift, especially if our distance indicators don't have such large precision. So this distribution fall very quickly after redshift of 0.1. So in data release 1, in December last year, we used data release 1 to make a measurement of the growth rate, and there's a batch of 7 to 8 papers that are already published. 2 of them describing the catalogs, 1 of them describing the 0-point calibration and the cross calibration of the magnitudes of those samples, and also a measurement of H0. There's 1 describing the catalogs of the mock catalogs we used to test the methodologies, and there's 3 papers with 3 different methodologies measuring the same thing from the same data sets. And lastly, there's 1 that's measuring the growth rate with a cross correlation only between DESI and Pantheon plus supernova peculiar velocities. So there's a very good internal consistency checks from fundamental plane and Tully-Fisher samples, and we used for the first time a large sample of mocks to test all methodologies. This is the footprint of data release 1. Maybe you've seen this before in other DESI talks, but I want to highlight here is the number of peculiar velocities from this sample already surpasses past PV samples just with 1 year of data. We also use the low redshift end of the DESI bright galaxy sample to as a density tracer, and we have this number of galaxies to do that. The mock catalogs that we have are based on n-body simulations, the Abacus Summit suite. We cut large boxes of 2 gigaparsecs on a side into smaller boxes, since our volumes are small, to make up for 675 realizations using full matter-only n-body. We place galaxies using an evolving HOD model from Smith et al. And then we apply observational completeness and things like that. And from the same sample of parent galaxies, we get the density sample, fundamental plane, and Tully-Fisher samples, all accounting with the cross correlations by construction. So this is the largest sample of mock catalogs and most accurate because it's based on n-body simulations for PV cosmology. So as I mentioned before, we have three methodologies: maximum likelihood estimator, and two which are the standard two-point correlation functions. The first one, the idea is that we have the density field in voxels, we put the survey in a mesh, and the same thing for the velocity field, and we assume that the correlations between them are given by Gaussian distribution. And so we write the Gaussian likelihood, a multivariate Gaussian, where the covariance matrix is a model that we have that depends on F sigma 8. So by varying F sigma 8 in this covariance, we can maximize this likelihood and extract what is the true value that's preferred by the data. We test this method with mocks. So this is a plot showing the F sigma 8 measurement and the relative uncertainty of each measurement. You can see that on average, those points align with the prediction from the mock. However, the scatter of those points is slightly larger than the estimated uncertainties of individual measurements. So we have to do some scaling of the uncertainties for this particular method. Making it more conservative and more robust. Here are an example of correlation function and Fourier space analysis. This is the monopole, quadrupole, and on the left you have correlation function, on the right you have power spectra. I'm comparing data with mocks, and this is the density functions, and here you can see the velocity or momentum, and here you have the cross correlation between density and momentum. This is just the dipole where most of the information is coming from. The model is based on perturbation theory and higher order bias expansion. I won't go into the details with the maths of this, but we test this method on our mocks, which are fully nonlinear with nonlinear biases, and we have an excellent fit to the power spectra to quite large scales, quite small scales, sorry. And we recover well the input F sigma 8 of those mocks. We didn't identify any bias in any of those methods that we used. So we are happy to proceed to use them on data. This is the measurement on our data, and we can see that the model is quite a good fit to most of the points. And for the velocity power, we had to remove some scale, some data, because we think that we identify some systematics that we don't know the source yet. So to be conservative, we cut those small scales that shown discrepancies with the model. So this is the measurement of F sigma 8 we have from the Fourier space analysis, and this is the full posterior with all the other nuisance parameters of this analysis, including bias and velocity dispersion parameters. And the dashed line here is the prediction from lambda CDM plus GR, and we are in good agreement with that for now. So this is this results, and we can compare it to the other results from the other methodologies. They're quite consistent with each other, and we derive a consensus result out of those three using the correlations between those methodologies based on measurements from mocks. Those correlations are shown here. They range between 27 and 38%, and we derive this consensus result, which corresponds to a 12% uncertainty, and this is the point, this is the field point here, the consensus result. Great, so we can look at the cosmological implications of this result, particularly the gamma parametrization of F, and here I'm showing the constraints on gamma, sigma 8, and omega m. The blue one is including high redshift F sigma 8 measurements plus BAO, while the orange or green here is the same data plus just 1 point of our growth measurements with DESI-1. So you can see how good is the reduction in the gamma uncertainty just by adding 1 point from us. Here are the numbers. Please disregard this preliminary. This is already published. You can see a 50% reduction in the uncertainties of gamma and slightly less, but some reduction of omega m and sigma 8 parameters. For now, this is all consistent with GR, but we hope in the future to see more strict uncertainties on gamma. Okay, so what's next? Obviously, we are waiting for DESI to finish taking data, and we expect a larger sample for DESI. But in Marseille, particularly, we are very interested in using future or current data sets of supernova. ZTF and LSST were produced thousands of supernovae across large portions of the sky, and they are less numerous than DESI, but they have better uncertainties in distance. So it's very interesting to do this measurement as well using type 1a supernovae. Here's a footprint plot showing the overlap between ZTF, LSST, DESI, and FORMOST. ZTF and DESI are in the north, while FORMOST and Rubin are in the south. And there's great opportunities to do a joint final ultimate measurement, let's say, of F sigma 8 using peculiar velocities. We did some forecasts in Marseille using actual analysis on simulations for ZTF and LSST, and we obtained this type of uncertainties. And this is just using peculiar velocity data. This is not considering redshift space distortions. But if you combine with DESI, there is a potential of great reduction of uncertainties in this redshift range. We also did some Fisher forecasts on the final measurement, combining north and south surveys, and we obtained something below 6%, but just assuming linear information, the 2-point function up to some value of Kmax. And this, of course, that can be extended to 3-point functions and any other statistics and more nonlinear scales. So to conclude, I hope I convinced you that peculiar velocity surveys are very interesting to test dark energy and modified gravity theories, and I presented you with this 12% growth measurement with DR1, and we are working hard on DR2 already. We expect this to be coming in the next few months, and we are very excited to use homogeneous samples of supernova to do this type of measurements. Thank you very much, and I'll hope to chat with you soon at the discussion session.